We're just about ready to add a lot of pieces to our grammar. We'll be able to add statements and method definitions and things like that. But if we just do it with the structure that we have right now, it's going to become very unwieldy. So one of the things in part 9 was in test util, we had this test print AST method that would take an AST node and then turn it into a string. And we would check and see if it was the expected output. And the way this works is by calling this print AST method. And this is using a switch, which is basically, it's a pattern matching switch. So it's essentially the same as having a bunch of ifs that say if root is instance of constant expression, else if it's instance of identifier expression, and so on. So this works okay when we only have 3 types and none of them are particularly complicated. But we're going to be adding, 30 more types as we build up the language, and this is going to get really out of hand. And we also need to add multiple methods that are going to do different kinds of processing on our tree, right? So one thing we want to be able to do is take our abstract syntax tree and turn it back into source code, but we also need to be able to go forward and turn it into VM instructions. And as it turns out, we're going to want to do some type checking, and it makes sense to do that separately from the compilation phase. So we're going to want to go over this tree 3 or 4 different ways, performing different operations. And we would have to duplicate this big structure for each one of those. So there's actually a design pattern that'll help us avoid that. It's called the visitor pattern. You may hear that we don't need the visitor pattern anymore because Java has this pattern matching in a switch. That's true for very simple cases like what we had in part 9, but that really would not be a very nice way of doing it once we have multiple visitors and they're complicated. If you want, once we add some more stuff to these visitors, once we have more things in our AST, so maybe after part 11 or 12, try going back and writing recursive code instead of the visitor classes that we have and make it do the same thing. And you'll see how it quickly becomes unwieldy. It gets big and nasty and very repetitive. So we're going to use the visitor pattern instead. The basic idea of the visitor pattern is that we can create a visitor object. Each visitor class will have some task that it's trying to perform. In our case, in this part, we're going to be writing the PrintVisitor, which knows how to turn the AST back into source code. And then each node in the tree, each of our AST classes is going to implement this visitable interface. And that means that it will have an accept method. So the visitor pattern or the visitor object will be given to the AST node, and then it will pass that visitor around the tree. So we'll give it to the root of the tree, and the accept methods will be used to pass the visitor around the whole tree. And as it goes around the tree, the accept methods in the various nodes will call visit methods on the visitor itself. And that's telling the visitor where we are in the tree traversal, and the visitor can then get some work done when those calls are made. So here's the visitor we're going to be using for this part. It will get larger and more complicated as we move forward. So as we walk around the tree, we may encounter a constant expression object. In that case, we'll call the visit method and pass that object in, and then the visitor can do something with that constant. If we encounter an identifier expression, the same thing happens. There's a visit method that's called when that happens. Binary expressions are a little more complicated because they have children. And as we move forward and add statement types and classes and method definitions and things, we're going to have many more of these more complicated instances that we have to deal with. With the binary expression, it turns out we'd like to be able to do something before we process its children. We'd like to be able to do something in between processing the children, and we'd like to be able to do something after processing both children. And so we have 3 visit calls that will be made at those 3 times. So when we first arrive at the binary expression, we will call previsit. Then we'll go pass the visitor down to the left subtree, and it'll get passed all around, and a bunch of other visit calls may be made. And then the visitor will eventually come back to this binary expression node, and we'll call visit. And then we'll pass the visitor around the whole right subtree, and when it comes back again, we will call post visit. So here's an example tree. We've got an add. Basically, these are binary expression objects. We have 4 different operations, so it's easy to tell them apart. We have a couple of identifier expressions and a couple of constant expressions. If we build this tree up, which we could do by parsing this expression, we could then give a visitor to the root of the tree, and it would get passed around, and visit methods would be called as we work our way around the tree. So here is the sequence of visit calls that would be made. So first we would call previsit on the plus node because we are first arriving at that node. Then we pass the visitor down to the left child, and we would call pre-visit on this node. We would pass the visitor down to its left child. We would call pre-visit on this node. Then we pass the visitor down here. Now this is an identifier expression node, so we would call that visit method here. Then the visitor gets passed back up to the parent. And now we're here for the second time, right? We've already processed the left subtree. Now we're going to call visit on this node. So notice there was a pre-visit call made on the modulus node. Now there's a visit call made on the modulus node, which will do something different than the pre-visit. Then we pass the visitor down to the right child. We call visit on our constant expression 5. We pass the visitor back up, and we make a post-visit call on the modulus node. We're here for the third time after processing both subtrees, and so post-visit is called. Then we go back up to the multiply node, and we're going to call visit because we're in between the two subtrees. We'll pass the visitor down here and call visit on our identifier y. Visitor gets passed back up, and we call post visit on the multiply node. Then we get passed out to the add node for the second time. So we call visit, pass the visitor down to the right child, pre-visit the division node, pass the visitor to z and call visit on that. Then we call visit on the divide node, pass the visitor down to 4 and call visit on 4, pass back to the divide node for the third time and call post visit, and then we get passed back to the add node the third time and call post visit. So you can see all of these calls, and if you work your way around the tree, you can figure out the order of the calls. One way to do this is to sort of drag your finger around the outline of the tree, and whenever you touch the left side of an internal node, you're going to call pre-visit. Whenever you touch the bottom, you'll call visit. And when you touch the right side, you'll call post-visit. So that's another way of sort of working this out. Basically, we would say pre-visit, 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 and then visit, and then visit, and then visit. And then we'd hit pre-visit here, and then visit, and then post-visit. I think I missed something. Pre-visit, 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 visit. Then we're hitting this for the second time, so visit. Then we hit this for the second time, visit. First touch is pre-visit, and then visit, and then post-visit, and then finally post-visit on the root. So you can do that however you like. Think about the way the except methods are structured, or work your way around a picture of the tree. It doesn't really matter as long as you get the order of those calls right. So what do we have to do in the code? The code in test-util in part 9 has been deleted and now uses a print visitor to turn the tree into a string. So the test from part 9 won't pass again until you've finished the code for this part. Part 10 doesn't have any new tests. We just need to get those part 9 tests to pass. The way we need to do that is we're going to have to build except methods in each of our AST classes. There is a base class called AST node, right? This now implements visitable, and that means that every AST class needs to implement except. The job of except is to call the except methods on its children and pass the visitor farther down the tree, and also to call the visit methods on the visitor to let it get its work done. So you need to get the ordering of these calls right. We're also going to implement the abstract visitor class, which will be a do-nothing implementation of the visitor interface. So many visitors don't need to implement all the methods in the interface because they don't need to do work at every possible point in time. Right? Each of those visit calls really represents a point in time as we traverse the tree. And some visitors will only need to do things at certain points in the traversal. So we're going to have a class called abstract visitor that implements the interface and just has empty methods for all of the visit methods. And that way, when we're writing a visitor, we can extend this and just override the methods that we need to implement. And then finally, we need to build the print visitor. We will need to put some code in each of the visit methods for this one. And there's also a get result method that will be called after the traversal, and it will return the string that was built up as we walked around the tree. Right? So basically, the print visitor will be passed around the tree, and as it goes around the tree, it will build up a string that is the source code that represents that AST. Keep in mind, visit methods should never call other visit methods. If you find yourself doing that, you're fighting against the visitor pattern. You also should never need to use instance of in your except methods. Think about ways that you can avoid that.